calibration, and final systems checkout. Following this, the aircraft underwent an extensive program of taxi trials. On May the 1st, 1972, with T. Edmonds, Chief Engineering Test Pilot of the Boeing Company, at the controls, the Augmentor Wing Buffalo became airborne for its first flight. The flight lasted 51 minutes and was quite uneventful. The pilot commented mainly on the similarity of handling qualities with those experienced previously on a flight simulator. Following this first flight, Boeing successfully performed 10 hours of flight trials, exploring the flight envelope and thereby demonstrated the airworthiness of the research aircraft. However, the short landing capabilities were not explored during this test phase. In July of 1972, NASA took delivery of the aircraft, and it was ferried to the Ames Research Center, Moffett Field, for the STOL flight research program. A total of 800 flying hours have been accumulated, documenting at first performance and handling qualities of the concept, followed by more general investigations into area navigation and terminal guidance of STOL aircraft. No major problems have been encountered, and the aircraft has established a very fine serviceability record. In general, the aircraft's handling and control characteristics are better than predicted. Longitudinal static stability, stick fixed, is positive above 60 knots for all flap and nozzle configurations, and approach configuration at low speed has been demonstrated with control power well within limits. Maximum roll control accelerations in excess of 0.5 radians per second squared and maximum roll rates of the order of 25 degrees per second have been demonstrated in the landing approach configuration at 65 knots. Flying has been performed both with and without stability augmentation about the lateral directional axes. Stability augmentation greatly improves turn coordination, but many STOL transitions and landings have been performed quite satisfactorily without the use of this aid. Flight evaluation of the power on STOL has shown good characteristics at all flap angles. With the flap angle set at 0 degrees, full trailing edge up elevator can be reached in the pre-stall buffeting phase, which effectively prevents further stalling of the aircraft. Similar characteristics pertain to the flap 30-degree configuration, where once again the aircraft reaches an angle of attack of about 35 degrees. Lateral directional perturbations commence at the onset of buffet, but bank angles of 10 degrees are not exceeded with normal coordinated use of rudder and roll control. With the flap at the 65-degree landing setting and in the latter stages of the stall, indicated speeds of 40 to 45 knots are reached at angles of attack exceeding 30 degrees. Immediately following the onset of buffet, the aircraft demonstrates a consistent nose-down pitch, which is accompanied by a sharp increase in indicated airspeed of 5 to 8 knots. Most of the flying time at the Ames Research Center has been concerned directly with the STOL performance of the aircraft, both into an airfield on a controlled glide path and out of the field with a maximum effort short takeoff. With engines at maximum takeoff power and a flap angle setting of 30 degrees, the aircraft becomes airborne with a ground roll of about 600 feet and climbs out with a gradient of 18 to 20 degrees. Initially, a ground-based visual glide slope indicator was used to provide guidance on approach, whereas subsequently the pilot was provided with a cathode tube display in the cockpit, which permitted operation under IFR conditions. Approaches were generally made on a glide slope of 7.5 degrees, that is over twice that of conventional aircraft, while approach speeds lay between 55 and 65 knots, depending on aircraft weight. Control of glide path has been studied using nozzle deflection with the power held constant and alternatively using throttle control with the nozzle fixed. Nozzle rotation has proved to be the more precise and responsive mode of glide path control, particularly where large glide path corrections are required. However, use of throttle control has also yielded satisfactory approaches. High-lift V-STOL systems often encounter some form of adverse changes to lift or drag when flying close to the ground due to impingement of the deflected jet. However, contrary to some expectations, the Buffalo Spey aircraft does not suffer a sudden loss of lift just prior to touchdown. And in fact, it can be flown in steady flight with the wheels only a foot or two above the surface of the runway. The single-engine failure case on takeoff has been simulated with the failure being initiated at the rotation speed of 60 knots by throttling one engine rapidly back to idle power. By the time the aircraft reaches 65 knots, the failed engine is essentially back to idle power, and the aircraft climbs out at a rate of 250 to 300 feet per minute with very small control forces experienced by the pilot. Similarly, the takeoff has been performed from a standing start on one engine. Climb speed is 75 to 80 knots at a typical weight of 42,500 pounds. The influence of a single-engine failure on approach to landing has also been simulated, following which recapture of the glide slope and continuation of the approach to a landing can be accomplished. Once again, trim forces experienced by the pilot are very low on account of the cross-ducting of blowing air to the wing. Transitions from cruise to landing approach conditions and from takeoff to cruise have presented no difficulty. Likewise, touch-and-go landings or wave-offs have proved easy to accomplish, due largely to the powerful and responsive thrust vectoring capability available to the pilot. Landings have been demonstrated in wind speeds ranging from 30 to 45 knots and with gusts of 10 to 13 knots. The indicated airspeed at touchdown ranged from 52 to 60 knots approximately, so that ground speed at touchdown was often extremely low. Horizontal wind shear was quite apparent, with the pilot reporting variations in indicated speed up to 15 knots within a 3 to 5 second period during the approach. Thus, the important benefits of powered lift for STOL operation in turbulent and gusty conditions have been demonstrated. The aircraft is far less dependent on wind velocity and wind variations than in the conventional case because of the blown wing. Furthermore, about 15% of the aircraft weight is supported directly by vectored thrust, which renders this component of lift completely insensitive to wind variations. Success of the large-scale wind tunnel and flight tests to date have laid the foundation for immediate development of a prototype jet STOL tactical transport, incorporating the Augmentor wing system. In late 1980, successful evaluations were conducted by pilots from the Department of National Defense, the United States Air Force, and the United States Navy. These tests have confirmed the potential for takeoff and landing ground roll distances of 800 feet or less. Furthermore, wind tunnel tests have demonstrated the intrinsic efficiency of the concept for energy conservation. The Canadian government is funding the project definition phase of an advanced STOL transport aircraft in a broad size range. A study of worldwide market requirements is underway with the expectation that ongoing programs could form the basis for international collaboration, leading eventually to the ultimate goal, the efficient combination of short field capability with the high subsonic cruise speed of modern-day transport aircraft.